Hello engineers, welcome back to another video. In this video, we are going to discuss motion planning for self-driving cars using a classical algorithm, Frenet frames. We are going to do our motion planning on a simulation-based Prius Robot Car. Let's have a look at that simulation. In this upper simulation window, we are going to see how the robot car is behaving, how it is moving and avoiding the different obstacles that come in front of it. In the lower window, we have the visualization. Here we will see what the robot car is detecting using its lasers, how it is detecting the obstacles, and what is the path that it needs to follow. First, we are going to run our simulation without any obstacles, and we are going to see in the visualization window how the robot car behaves. In the next step, we will add some obstacles and then see how the robot car is behaving in the simulation as well as in the visualization. So let's go. Let us first run our simulation without any obstacles in front of the robot car. Now let us add some obstacles in front of the robot car and see how the algorithm behaves. As we can see, the robot car was given a global path to follow in blue color. However, due to the motion model of the car and the obstacles present in the global path, the robot car was not able to completely follow the global path. Hence, the algorithm derived certain other different paths in green color that were not only able to avoid the obstacles and obey the constraints, but also follow the global path that was given. This kind of algorithm is also useful for dynamic obstacles where the obstacles are moving and changing their positions with time. This kind of scenario is very similar to a self-driving car driving on a highway where the car has to avoid and overtake the traffic. So now let us discuss the technical details behind the Frenet frame algorithm and understand how it makes the self-driving car to do so. Alright, so the problem of motion planning can be divided into three stages. Let us understand these three stages using a personal example. Let us suppose that we have decided to go for a picnic. The first step to go to a picnic spot would be to see a map and determine all the roads, all the intersections and all the turns that we need to take to start from our house and reach the picnic spot. This high-level based planning in which we used a map to determine the path is what is called the global path planning stage. This is the first and the most high-level path planning task. Once we have decided the path, we get in our car and start driving. While we are driving our car, which road to take next, which intersection to take next becomes a secondary task. The primary task in this part is to actually be able to navigate through the road that we are currently on while avoiding all the different traffic and obstacles. At times we need to stop our car, we need to slow down our car, or even we need to overtake the other cars that are in front of our car. This is a lower level of the path planning architecture which is called the local path planning. In this step, we are more concerned with how we navigate through the actual path that we are currently on. In the next step, once we know which maneuver we want to do, either we want to stop the car or we want to overtake the other car, we want to decide upon how much velocity we need to give to the car and how much steering we need to turn. This part comes under the control part, which is the lowest level in the hierarchy of our motion planning algorithm. Frenet frame trajectory generation comes under the second level of the motion planning architecture, which is the local path planning. We already have a global path that we need to follow. This Frenet frame algorithm helps us to follow that global path. Local path planning for almost all the robots need to have a specific obstacle avoidance mechanism. Generating a global path, we can avoid the different static obstacles that are present in our way. However, to avoid the dynamic obstacles, the obstacles that change their position with time, local path planning algorithms need to have this obstacle avoidance. And this is very true for any self-driving car. Once we are at an initial position, we use our motion planning algorithm to determine the path that we need to follow. Once we have generated the path, we follow that path for first few time steps. After those first few time steps, we again call the motion planning algorithm to generate a new path. Once we have that generated new path, we again follow that path for first few time steps. This generation and following keeps on going until we reach our destination. This kind of path planning is called the receding horizon based path planning and is very common in such local path planners. Frenet frames are actually a coordinate axis that is used to represent the position of an object in space. Let us consider this example over here. We have this road in green and we have a global path in black that our self-driving car needs to follow. Considering the case of the traditional Cartesian coordinates, we are going to have our origin present somewhere over here, and we are also going to have a coordinate frame that is fixed on our self-driving car. Every point on this global path will be represented with respect to this coordinate frame. We are going to have a curve dependent on the values of x and y. In the Frenet frame, we have the coordinate axis that is defined with respect to this curve that we already have. We represent the two coordinates using s and d. S represents the distance that we have traveled along this curve and d represents the deviation that we have perpendicular to this curve. Consider this example. If we represent this as s equals 0, as we move along this curve, we increase the s as it increases from 1 to 3. D represents the deviation perpendicular to the curve. If we are at the center line, then we have d equals 0. If we slightly deviate to this side of the curve, then we have increasing d equals 1, d equals 2. If we go to this side of the curve, then we have d equals minus 1 and d equals minus 2. Now, as we can see, Frenet frames are actually a more convenient and natural way to represent a path that we need to follow along a curve. This S and D actually allows us to separate the motion planning along the curve and perpendicular to the curve. Now, there is a simple mathematical relation that we can use to convert between these two coordinate frames. We have this red colored global path over here and we have this blue colored path that the car is actually following. Any position on this reference path is represented using r of s and any position on the actual followed path is represented using x. A perpendicular line drawn from the reference to the actual followed path has a length d and its direction is denoted using the vector n. The relation between these quantities is as written over here. In a 2D scalar form, the vector x can be represented using two coordinates x and y. Using s, we can derive the position of a point r in the x and y axis, ix and iy. The distance d is already a scalar value. Vector n is a unit vector whose direction can be determined using the angle theta plus pi by 2. Theta over here is simply the yaw or the tangent angle of this reference path. The complete relation in 2D can be represented using the equations given over here. Converting from the x and y coordinates to this Frenet frame is also simple. It is just the reverse process of what we have done over here. We simply need to find the smallest distance vector connecting x and r. The Frenet frames over here help us describe the path that the robot needs to generate and as well needs to follow. The actual path actually consists of polynomials. The whole process works something like this. In the S and D coordinate frames, we derive a number of different polynomial paths, like we can see over here. These polynomial paths are generated by varying certain initial or final conditions. From these paths, the path that avoids the obstacles and minimizes a given cost function is chosen as the path to follow. Then the robot needs to give control commands to its motors to actually follow that path. Let us now see how this polynomial path generation is done. Consider a simple case where we are given the initial position and the final position represented as P0 and Pf. The simplest polynomial that we can fit between these 2 points is a line. A line is simply a polynomial with degree 1. In the second case, we are not only given the initial and final positions, but we are also given the initial and final speeds. The smallest polynomial that can be fit between these initial and final conditions is a cubic polynomial. A cubic polynomial has 4 variables: ax cube, bx square, cx and d. These 4 variables can be solved using these 4 conditions that we are given over here. Correspondingly, we are going to have a single cubic path between these initial and final positions. In the third case, in addition to the speed and position, we are also given the accelerations. In this case, the smallest polynomial that can be fit between the initial and final states is a quintic polynomial, a polynomial of degree 5. A 5-degree polynomial has 6 variables. These 6 variables can be satisfied by these 6 constraints. Now consider another case where we slightly reduce the problem and remove one constraint from these 6 constraints. Hence, we now have 5 constraints that we need to follow. For these 5 constraints, we can fit a quartic polynomial, a polynomial of degree 4, which has 5 variables. Hence, any combination of these initial and final states can be solved using a corresponding polynomial which has equal number of variables as the number of constraints. For the d-axis, we would already have the initial 3 conditions: d, derivative of d, and the second derivative of d. For the final states, we want to ensure that the derivative of d is 0 and the second derivative of d is also 0. That is, finally there should be no motion along the d dimension. By varying the final value of d, we can generate a number of different polynomials. For instance, we can have a polynomial with final d as 0, final d as 1, or even final d as -1. The polynomial generation is also dependent on a parameter t, which is the time it takes to follow that trajectory. For the s-axis, we only have 5 constraints. The initial 3 constraints are already known to us: initial s, the speed s, and the acceleration along s. In the final state, we do not have any constraint on what should be the final value of s. However, we have some constraints on the velocity along s and the acceleration along s. Now, this complete algorithm that we are discussing is only based on one particular highway scenario that a self-driving car has to face. A self-driving car, while driving on a highway, sometimes needs to stop, sometimes needs to merge between 2 vehicles, and even sometimes needs to overtake the other vehicle. The behavior that we are discussing over here is only the overtaking behavior. Mathematically, this behavior can be modeled using constant velocity. For this scenario, we want our car to only go and maintain a particular speed. If we want our car to maintain a particular speed, whenever an obstacle comes in front of the car, The only way the car can maintain its speed is to overtake that obstacle. Since we want a constant velocity, the acceleration along the s direction needs to be 0. Also, due to the constant velocity, the final s can take on any value since we do not have a final destination in mind. To generate a number of different polynomials in the s direction, we vary the final velocity and the time. If we want our car to maintain, let's say, 40 kilometers per hour, then we are going to vary the final velocity by approximately 10 to minus 10 units. Hence, starting from the range of 30 till 50 kilometers per hour, we are going to generate different polynomials. Once these polynomials along the d direction and along the s direction have been generated, now our task is to select the best polynomial from these. We independently need to select the best polynomial for d and the best polynomial for s. Once we get these, we combine them to generate a final s and d based path. The best polynomials are retrieved using cost functions. We have separate cost functions for d and s, as we can see over here. Their structure is almost similar. We have three terms. The first term is the jerk, the second term is the time, and the third term is the final state. Mathematically, jerk is represented as the triple derivative of position, which is also the derivative of acceleration. Physically, jerk represents the ease or comfort that a person has while sitting in a car. If we have sudden accelerations and deaccelerations, it would not be comfortable for any person sitting inside the car. Minimizing the jerk smooths this behavior, hence we have this present in our cost function. We also need to minimize the time it takes for the car to follow a given trajectory, hence we have this time parameter over here as well. For the d cost function, we have this final term d square over here. Our objective for the self-driving car is to follow the reference path completely. While we move on our road, we do not want our self-driving car to deviate much from this reference path. To minimize this deviation behavior, we have this d square term over here. In the s cost function, we have this s dot minus s dot d whole square term. Since we want our self-driving car to maintain the particular velocity that we have given, this term penalizes those trajectories that have speeds deviated from the actual commanded speed that we want. Before calculating the cost function for all the different paths, the first step we do is obstacle avoidance and introduce certain other constraints. For instance, if we have an obstacle over here, something like this, then these three generated paths will be immediately discarded. We can also discard some other paths that do not follow certain constraints like crossing velocity limit or crossing the curvature limits. Finally, from the remaining paths, we calculate the path that minimizes these cost functions and give that to the robot to follow it. Alright, so this is it that we had to discuss for Frenet frame based optimal trajectory generation. Now let us have a brief look at the code. All the code that we are going to discuss is already uploaded on GitHub, and the link to that would be in the description box below. The main implementation of the Frenet frame algorithm is present in these two files, polynomials.cpp and Frenet optimal trajectory.cpp. Let us first have a look at the polynomials file. Here we have the QUINTIC polynomial class that takes in as input these 6 conditions: initial position, initial velocity, initial acceleration, and final position, final velocity, and final acceleration. It also takes in this parameter t, And using all these parameters, it derives a quintic polynomial path. Using these mathematical calculations over here. Then we have certain functions of these quintic polynomials that calculate the point, first derivative, second derivative, and third derivative. Similarly, we have this class for quartic polynomials where we take in initial position, velocity and acceleration, and final velocity and acceleration. The final position is taken as a variable over here. And we also take in time as an input. We do some mathematical calculations over here and derive the quartic polynomial. Here we also have the calculation functions, calculate point, first derivative, second derivative, and third derivative. Now let us have a look at the Frenet optimal trajectory program. Here we have this function Frenet optimal planning that actually computes all the path and gives us the final path to follow. During implementation, as we discussed, the robot calculates a path, follows it for some certain time, and again recalculates the path and then follows that new path. In this iterative manner, the path planning goes on. Hence, for each iteration, we are going to have different initial conditions, like different initial S, different initial velocity in S, different initial D, and different initial derivatives of D. These are taken as inputs over here. We also take this spline 2D structure as well. This spline 2D structure is the actual reference path that we need to follow. In this part of the code, we generate the different Frenet-based optimal paths. We sort those paths by their cost. Then based on the path that satisfies all the obstacle avoidance and curvature-based constraints, we take that as the best path and finally return that path. Let us have a look at the generation function. In the generation function, we take as input all the different initial conditions. Now for the D-based path, we have these three nested for loops. The first loop varies the final D. The second loop varies the T or the time. Then this final loop varies the final velocity in D only by a small value. Then we generate some polynomials based on these conditions and put them in a list-based format. Similarly, we do this for the S coordinate as well, where we have two nested for loops. The first varies the time t and the second varies the target speed. Now let us have a look at how these S and D polynomials are generated. Here we have the function to calculate the D-based polynomial. Here we simply call the quintic polynomial class that we discussed before. Then we store all the related values like the time t, the value d, the first derivative of d, the second derivative of d, and the third derivative of d in a discretized list-based format. Then we sum up the discrete third derivative of d, which is the jerk. Using this value of jerk, we calculate the final cost that is for the D polynomials. Here we can see the jerk term, the time term, and the D squared term. Similarly, for the S polynomial, we generate the quintic polynomial, store its different related values in a discretized list-based format, calculate the jerk, and finally calculate the cost function related to that, which is the jerk term plus the t term, the time term, and the difference in S. Let us also have a look at the code that transforms from the Frenet frame to the global X and Y coordinate frame. Over here, we take in the cubic polynomial spline as input. We calculate the X and Y position of that reference path. Then we calculate the yaw, which is the angle. And then we calculate the X and Y. This change in the sine and cosine is due to the addition of the pi by 2 term, which is taken care of implicitly over here. Finally, in the below code, we discretize all the different values that we calculated and store them in a list-based format. These global X and Y coordinates are then sent to the controller part of the self-driving car. The controller part can then on its own decide how to follow those given X and Y points. Since robots do not have big computers that are present on their system, they have a very small computer with a limited compute power. Hence, the algorithm made for those computers should be optimal in terms of memory and time. The constraint is not only on the compute, but also on the physical environment. If the robot is not able to perform all the calculations in time, it would eventually crash into an obstacle. This Frenet frame method over here is quite optimal and can be made to run fast by using certain optimizations and parallelizations. All right, so this is it that we had to discuss for this video. If you liked the video, press the like button and subscribe to the channel for more such videos. And thank you for watching. Bye.